Hello everyone out there. My name is Tushar. So for this competition I have taken this topic energy aware eVTOL hover modeling using Simulink. So this slide basically summarizes the whole architecture of my project. So I have an altitude controller which regulates hover, and the hover dynamics translate thrust demand into electrical power demand. And then this power demand is then supplied by battery system supervised by a battery management system known as BMS, which enforces safety limits and power constraint. So as a result, it can be termed as flight control constraint by battery safety. So now I will demonstrate how this architecture is implemented and validated in Simulink. So this is the complete integrated Simulink model. So this part over here is the flight dynamics part of it, and this part over here is the battery management system. These are being connected using this interface known as power to current subsystem. So now the altitude controller basically here generates the thrust command to maintain hover, and the hover dynamics convert this thrust command into the electrical power demand. And then the battery and battery management system then determines whether this power can be safely delivered to the system or not. This creates this creates a closed loop system where energy availability directly affects flight behavior. So as I have told, this is the flight side of it, and altitude reference is there, which basically gives the desired altitude requirement. So for my case, I have taken it 5 units, and the here the altitude controller will generate the thrust output out of it, which gives the input to this hover dynamics, which ultimately generates the electrical power demand. So these blocks captures the dynamics of the eVTOL and computes the corresponding electrical power required. And and how they do is we have the required Simulink mathematically modeled over here. As we can see, this is our altitude controller, which has the PI controller, PID kind of thing. And then we have the hover dynamics over here, which also follows the similar mathematical thing, and which goes to this interface, and the electrical power demand is converted into a battery current command using this terminal voltage. This basically represents the inverter and motor interface, allowing the flight controller's power demand to be expressed as a current request to the battery system. So this will convert into the uh, current which is compatible to our BMS system. So now we'll run it for the 300 seconds to check the scope sort of it. So now, so under normal conditions, the vehicle achieves stable hover. So as we can see, our uh, altitude scope, as it there is a little overshoot over here, but then PI controller stabilizes it to the 5 units, which is our required altitude. And let's see our electrical curve, which says like it stabilizes after the initial transient and then have a constant value, so which is like a positive sign out of it. And then we have the state of charge. So if we check the state of charge, it gradually decreases, so which is the required behavior from our system. And now let's check the battery temperature, as BMS at for BMS temperature is one of the important parameters. So as we can see, temperature increases as the system progress, so which is a desired, which is like the uh, kind of obvious thing that has to happen. And yeah, so the temperature rises slowly, and since all the safety limits are respected, the BMS will show the full current delivery. So as we can see, it has one basically means the true, so it is showing that all the current is being passed to the system. Now to validate safety behavior, I initialize the battery at a critically low state of charge. So now to check the validation of our model, we can change our SOC limit over here, so which is state of charge limit. So if I give it as a 0.15, which is a low state of charge, the emergency flag will open up. So there will be no current passed to the system. So if I do it and then I'll run it again for 300 seconds. So in this case, the BMS detects an unsafe condition. So we can see over here, it shows 0, which basically means the false. So it will not allow the current to pass to the system. Similarly, we can have the disposal power delivery, which also disables the power delivery. As we can see, it remains constant, so which doesn't make sense. So over here we can and then uh, if we check the I allowed, it also is 0, so the no current is being passed. So if we check the emergency flag, it shows 1, which means the emergency is active now because we have the low state of charge. So that's how it worked. And in a summary, this project basically demonstrate an energy aware eVTOL hover model where flight control performance is directly constrained by battery safety and endurance limit. Thank you.